Hi, everyone. Welcome back. Now we'll be going into thermochemistry. So thermochemistry is exactly what it sounds like. Thermal, thermometer. We're talking about heat transfers and temperatures. And so in this case, we have a few terms to clear up. So first, as you know, as you're probably familiar with, we have temperature, which measures the average amount of energy in a system. And we can measure temperature directly using a thermometer. And temperature measures heat. However, we also have these other two terms that maybe you don't remember, that are entropy and enthalpy. So entropy is the disorder inside of a system, and so that can be dictated by heat, by pressure, by volume. I like to think of entropy of a system like particles in a box. So let's say I have 1, 2, 3 particles in a box, and in another box, I have it's the same kind of particle, but I have a lot more. So in this box on the right, it's a much more disordered system, right? There's a lot more particles inside of that box, and they're all banging into each other, and there's just a lot going on. So the box on the right has a greater entropy than the box on the left. And then enthalpy is the total heat content of a system, and it is related to temperature, as temperature measures energy in a system. Both entropy and enthalpy are related to temperature through equations that we'll see in the next slide. And then we also have Hess's law that states that total enthalpy change during a reaction is independent of its steps. So you can have, by that, you use Hess's law to you can find the total energy in a single reaction with the reactions that make up that overall reaction. So continuing on about thermochemistry, we can derive relationships between enthalpy, which is delta H, and entropy, which is delta S. And so this is through the Gibbs free energy equation, which is delta G is equal to delta H minus temperature times delta S. And so this delta G is what's called Gibbs free energy, and that just is the energy that's available to do useful work in its system. It's the energy we can take to actually do something. And so we know that if delta G is less than 0, so it's negative, it would be it's considered spontaneous and is exergonic. And if delta G is positive, it's endergonic, and is non-spontaneous. And by spontaneous, it means that it's exergonic, it's going to release energy, and you don't need to add energy in the system to make this reaction or occurrence happen. So it's not spontaneous. So it is spontaneous, it'll happen on its own. If delta G is positive, it's endergonic, it needs energy to be entered into the system. And so it's not going to happen spontaneously on its own. And so following the chart, you can decide whether a process that we're talking about will be spontaneous or non-spontaneous. Here are some examples of how to use Hess's law. So let's look at that first one together. So as said before, the delta H of a system is independent of its steps, but you can add up the steps because it doesn't matter what order this actually happens in. We can add up the steps to get delta H of a total reaction. So in this first problem, we're told that we want to get this top reaction. We want to know what the change in enthalpy is when this reaction happens. And they give us 3 separate reactions that we know the delta H of. And so we can combine these reactions I bracketed in purple in order to get the reaction in pink. So let's see. In our first reaction, in the purple, we have N2 plus O2 to 2NO. So we know that we have NO as a product. So I can leave this reaction on the bottom as is. However, when I write it out, you can see that I don't make enough NO, right? I have 2 here, but I need 4. So all I'm going to do is multiply this guy by 2. And then I get 2N2 plus 2O2 gives me 4NO. And now this 4NO is in agreement with what I have in my goal reaction. So now at least I have one product. Moving on. In the third equation, I create H2O. And in no other place in the reaction in any of the other reactions do I have H2O. But I know in my final reaction, I need to have H2O, right? So I know that I can leave this guy as is, and he's also going to be part of the large addition of reactions. So I have in that reaction, H2 plus 1/2 O2 gives me H2O. But once again, I need 6 H2Os and I only have 1, right? So I need to multiply this reaction by 6. And then I get 6H2 plus 3O2 gives me 6H2O. And now, once again, this 6 is in agreement with the 6 here. So we're good to go. If I were to add up the reactions that I have right now, I would have a bunch of extra stuff I don't need. For example, in this pink bracketed final reaction, we don't have any H2, right? However, I do have H2 here and nothing to cancel that out. So that's when the second reaction comes in handy, because I know that in my final reaction, I don't have H2, I don't have this H2, I don't have N2, and I don't have, and I am missing NH3. And the only place I can get NH3 is the second reaction. So I know I'm going to have to use it and probably reverse it, as 2NH3 is a product, but it's a reactant in my final reaction. So I can just flip this to go the opposite way. So to make some space, once again, just before we keep moving, just to backtrack, we left this reaction as is, and we multiplied it by 2 to get that 4NO. And since we multiplied the reaction by 2, we have to multiply this delta H by 2. And then on the third reaction, we multiplied by 6 to get the 6H2O. And so we multiply this delta H also by 6. So now we have N2 plus O2 goes to 2NO, but we multiplied by 2. So we have our 2, and our 4. And then the third reaction, we did 6H2 plus 3O2 goes to 6H2O. And in the final reaction, we not only need to flip it, but because we need this NH3 to be in agreement with this NH3, but we need to multiply by 2 as well to get this 2 equal to this 4. So if we flip it and multiply by 2, we get 4NH3 to 2N2 plus 6H2. And since we flipped the reaction, well, as we said, we multiplied by 2 and we flipped it. So instead of multiplying just by 2, we multiply by -2 to the delta H value. Because all these delta H values are negative. And if it's a negative delta H value, it means that lost enthalpy in having the reaction happen. And so it gave off energy, so it's exothermic. And so the reverse, making this arrow reverse, if going to the right, we release energy, going to the left, we need to take in energy. So it becomes a positive delta H for the opposite reaction. Now, if we keep going to our addition, if we add all of these reactions together, we end up with, let's see, so we have 2 and 2, which cancels with the 2 and 2 down here. So we have these guys cancel. Then we have 2O2 plus 3O2, giving us 5O2. Then we have 6H2, but that cancels with the red 6H2 on the right of the arrow. And if things are on the opposite sides of those arrows, it means the reactant is also a product and we can cancel them. And the final reactant we have is just the 4NH3. And as for products, nothing else to cancel. We have 4NO plus 6H2O, which is exactly the reaction that we were given. So now we have to proceed and find what delta H's of this reaction, which we just sum the delta H's with our manipulations. So if we number this 1, 2, 3, our delta H is going to be 2 times delta H1 plus negative 2 times delta H2 plus 6 times delta H3. And when we plug in our numbers, it's going to be 2 times negative 180.5 kilojoules minus 2 times negative 91.8 kilojoules, running out of space. And then we do plus 6 times negative 241.8 kilojoules. And when we sum those all together, we get our delta H of reaction. And you can try that next one on your own.